Look up at the night sky, past the familiar twinkle of stars, and imagine a solar system unlike our own. Picture worlds where gas giants hug their suns so close they complete an orbit in days, where twin suns set over molten landscapes, and where tidal forces stretch planets into egg-shaped oddities. Now ask yourself this: why does our solar system, with its neatly spaced planets and gentle orbits, seem like the cosmic exception rather than the rule? The answer might just redefine how special Earth truly is. Today, we're embarking on a journey to compare our celestial neighborhood with the thousands of exoplanetary systems discovered so far, uncovering why ours stands out in a universe teeming with chaos. From Jupiter's silent guardianship to Earth's Goldilocks perfect position, we'll explore the delicate balance that makes our solar system a cosmic rarity. Stick around. By the end of this video, you'll see our corner of the galaxy in a whole new light, and who knows, you might never look at the night sky the same way again. To truly appreciate our solar system's uniqueness, let's take a closer look at its remarkable architecture. At the heart of it all is our Sun, a middle-aged yellow dwarf star that makes up over 99% of the solar system's total mass. Unlike the unstable red dwarfs or bloated giants found elsewhere in the galaxy, our Sun provides just the right amount of steady warmth and light, creating the foundation for everything that follows. Surrounding this stable anchor are 8 diverse planets, each with distinct personalities and stories to tell. The inner solar system is home to 4 terrestrial worlds: Mercury, Venus, Earth, and Mars, rocky planets with solid surfaces where temperatures and conditions vary dramatically. Beyond them lies the asteroid belt, a collection of rocky remnants that never coalesced into a planet, acting as a natural divider between the inner and outer realms. Venturing further out, we encounter the gas giants Jupiter and Saturn, massive worlds composed mostly of hydrogen and helium, along with their intricate families of moons. These planetary heavyweights shape the entire system's dynamics, with Jupiter in particular playing cosmic defense against incoming comets and asteroids. Farther still are the ice giants Uranus and Neptune, worlds rich in water, ammonia, and methane ices, where winds scream at supersonic speeds, but our solar system doesn't end there. Beyond Neptune lies the Kuiper Belt, a distant ring of icy bodies including dwarf planets like Pluto. This region is a frozen time capsule from the solar system's earliest days, preserving clues about how planets form. Extending even farther is the Oort cloud, a vast spherical shell of icy debris stretching halfway to the next star, occasionally sending comets inward on long, looping orbits. What makes Earth particularly special is its position within the habitable zone, the narrow band around the Sun where temperatures allow liquid water to exist. Not too close to boil it all away, not too far to freeze it solid. This delicate balance, combined with our planet's protective magnetic field and stable climate, creates the perfect conditions for life to thrive, a rarity in the cosmic ocean of exoplanetary systems. As we continue our journey, we'll see just how unusual this orderly structure is compared to the chaotic arrangements found around other stars. Now that we've toured our own cosmic neighborhood, let's venture beyond to explore the strange and diverse worlds orbiting other stars. Exoplanetary systems, planetary families around distant suns, are nothing like what we see at home. These alien systems challenge our assumptions, revealing a universe far wilder than we ever imagined. The hunt for exoplanets began in earnest in the 1990s, and since then, we've discovered over 5,000 confirmed worlds, with thousands more candidates waiting to be verified. But how do we find something so small and faint next to the blinding glare of a star? Scientists use clever tricks like the transit method, where a planet crosses in front of its star, causing a tiny but detectable dip in brightness. Another technique, radial velocity, measures the star's subtle wobble as an orbiting planet's gravity tugs it back and forth. There's also direct imaging, where advanced telescopes block out starlight to capture faint planetary glimmers, though this works best for young, hot worlds far from their stars. The diversity of these systems is staggering. Take TRAPPIST-1, a red dwarf star just 40 light-years away with 7 Earth-sized planets crammed into orbits smaller than Mercury's. 3 of these worlds sit in the habitable zone, but their closeness to the star means they're likely tidally locked, one side eternally scorched, the other frozen. Then there's Kepler 186f, the first Earth-sized planet found in another star's habitable zone, but its dim red sun bathes it in perpetual twilight, a far cry from our sunlit skies. Some systems defy logic entirely. Hot Jupiter's gas giants blistering close to their stars shouldn't exist based on our solar system's model, yet they're common, suggesting planets can migrate inward after formation. Others, like PSRB 1257+12, orbit a pulsar, a dead, spinning star that bathes its planets in deadly radiation. And then there are rogue planets untethered to any star, drifting through the galaxy's icy darkness. What's clear is that our orderly solar system is the exception, not the rule. Most exoplanetary systems are chaotic, crowded, or wildly unbalanced, proof that nature's imagination outstrips our own. As we peer deeper into the cosmos, each discovery reminds us just how special our quiet corner of the universe really is. Now, let's turn our attention to the heart of our solar system, the Sun, and why it's far more remarkable than it seems at first glance. While it may appear ordinary, our Sun is actually a cosmic rarity, a key ingredient in the recipe that makes our solar system so unique. The Sun is classified as a G-type main sequence star, often called a yellow dwarf. But don't let the term dwarf fool you. It's anything but small in significance. G-type stars like ours make up only around 7% of the stars in the Milky Way. The vast majority of stars are red dwarfs, cooler and dimmer than our Sun, or massive giants that burn bright and fast. That alone makes our Sun somewhat special, but its true value lies in its stability and longevity. Red dwarfs, the most common stars in the galaxy, are notorious for their turbulent nature. These stars frequently unleash violent flares, bathing their planets in intense radiation that could strip away atmospheres or sterilize surfaces. Planets in their habitable zones are often so close that they become tidally locked, with one side perpetually scorched and the other frozen in darkness. While red dwarfs can live for trillions of years, far longer than our Sun's estimated 10 billion-year lifespan, their erratic behavior makes them far less hospitable for life as we know it. On the other end of the spectrum are massive stars like O-types and B-types. These giants shine with blinding intensity, but they burn through their fuel in just a few million years before exploding as supernova, far too quickly for complex life to develop. Their planets, if they survive, are often left orbiting the remnants of these cataclysmic deaths, like neutron stars or black holes. Our Sun, however, strikes a perfect balance. It provides just the right amount of energy, not so much that it fries nearby worlds, and not so little that it leaves them in perpetual cold. It's also remarkably stable, with a relatively calm magnetic field and predictable cycles of activity. This steadiness allows planets like Earth to maintain stable climates over billions of years, giving life the time it needs to evolve and thrive. Even among other G-type stars, our Sun stands out. Many stars of similar size are part of binary or multiple star systems, where gravitational chaos can disrupt planetary orbits. Our solar system, with its single, well-behaved star, avoids these complications entirely. The Sun's lifespan is another critical factor. Its 10 billion-year main sequence phase provides an unimaginably long window for life to emerge and develop. Compare that to the fleeting existence of massive stars or the turbulent, slow-burning red dwarfs. and it's clear why our sun is such a precious cosmic rarity. So the next time you step outside and feel its warmth, remember, you're basking in the light of a star that's not just ordinary, but one of the universe's finest candidates for nurturing life. And that's a gift we're only beginning to fully appreciate. Now, let's zoom out from the sun and take a look at the way our solar system is arranged, because the orderly dance of our planets is another key piece of the puzzle that makes us unique. While many exoplanetary systems are crowded, chaotic, and full of extreme orbits, ours is a model of stability and precision. Picture our solar system as a well-organized neighborhood, with each planet keeping a respectful distance from its neighbors, moving in nearly circular paths around the sun. Mercury, Venus, Earth, and Mars orbit close to the sun in the inner solar system, while the gas giants Jupiter, Saturn, Uranus, and Neptune reside much farther out. The asteroid belt sits neatly between Mars and Jupiter, acting more like a gentle divider than a hazard. Even the Kuiper belt and Oort cloud, home to icy bodies and comets, are located at safe distances, their orbits carefully balanced by the sun's gravity. Now compare that to what we've found in exoplanetary systems. Many of them are packed with planets orbiting their stars at distances that would make our solar system seem like a vast, empty desert. Take hot Jupiters, for example, gas giants like Jupiter but scorched by their proximity to their host stars. These planets orbit so close that some complete a full revolution in just a few days, with surface temperatures hot enough to vaporize metal. In fact, the first exoplanet ever discovered, 51 Pegasi b, is a hot Jupiter so close to its star that its year lasts just 4 Earth days. What's even more striking is how often we find planets with wildly eccentric or oval-shaped orbits. Unlike our planets, which follow nearly circular paths, many exoplanets whip around their stars in extreme ellipses. One moment they're freezing in the outer reaches of their system, the next they're plunging dangerously close to their star, subjected to blistering heat. This kind of chaotic movement would make stable climates, and by extension, life as we know it, nearly impossible to sustain. Why the difference? The answer might lie in how these systems formed. Our solar system appears to have had a relatively calm, gradual development, with planets forming in place and gently settling into their current orbits over time. But many exoplanetary systems seem to have experienced violent upheavals early on, with gravitational tugs from nearby stars, runaway gas giants migrating inward, or even planetary collisions reshaping entire systems. These chaotic events leave behind the crowded, erratic arrangements we observe today. The takeaway: our solar system's orderly, well-spaced planetary orbits aren't just a lucky break. They're a critical factor in Earth's ability to sustain life. Without this careful arrangement, the delicate balance of our climate, seasons, and even the protection offered by Jupiter would be thrown into disarray. And that leads us to the next piece of the puzzle: the role our gas giants play in keeping the solar system safe. Now, let's turn our attention to one of the solar system's most influential guardians, Jupiter. This gas giant isn't just a spectacular sight in our night sky. It's a cosmic bodyguard playing a critical role in protecting Earth and the inner planets. Think of Jupiter as a gravitational shield, its massive presence diverting countless comets and asteroids that might otherwise threaten our home. Without it, Earth's history, and perhaps even the existence of life, could have been very different. Jupiter's protective power comes down to its sheer size and gravity. With a mass 2.5 times that of all the other planets combined, it acts like a gravitational sinkhole, pulling in or slinging away dangerous space debris. A famous example is the Shoemaker-Levy 9 comet, which shattered into pieces and crashed into Jupiter in 1994. Had Jupiter not been there, those fragments could have been on a collision course with Earth. But Jupiter isn't just a passive defender. Its gravity also stabilizes the asteroid belt, preventing larger objects from careening inward toward the rocky planets. In many ways, it's the reason our solar system feels so orderly and safe. Now, compare this to what we see in exoplanetary systems. Many gas giants there don't just stay put, they migrate. These wandering giants often spiral inward toward their stars, wreaking havoc as they go. Imagine a Jupiter-sized planet plowing through the inner solar system, its gravity flinging asteroids in all directions or even pushing smaller planets out of orbit entirely. That's exactly what happens in systems with hot Jupiters. Their inward migration can destabilize or even destroy any rocky planets that might have once existed in the habitable zone, turning a potentially life-friendly system into a chaotic battleground. Even worse, some exoplanetary gas giants end up in eccentric orbits, swinging wildly close to their stars before hurtling back out. This gravitational tug of war can strip away atmospheres, trigger extreme volcanic activity, or leave smaller planets tidally locked, one side perpetually scorched, the other frozen. In contrast, Jupiter's stable, distant orbit ensures Earth's environment remains relatively calm. No blistering tides, no atmosphere ripped away by a passing giant, just a steady, life-friendly rhythm. The difference couldn't be starker. While our solar system's gas giant acts as a protector, many exoplanetary counterparts become agents of chaos. This isn't just a matter of luck, it's a key reason Earth has had the stability needed for life to flourish. And that brings us to another vital piece of the puzzle: the precise conditions that make our planet not just habitable, but uniquely suited for complex life. Now, let's zoom in on one of the most critical factors that makes Earth so special: its perfect place in what scientists call the habitable zone. This is the sweet spot around a star where conditions are just right for liquid water to exist on a planet's surface. Not too close to the star where water would boil away, and not too far where it would freeze solid. It's often nicknamed the Goldilocks Zone because, like the porridge in the fairy tale, it's neither too hot nor too cold, but just right. Earth orbits right in the middle of our Sun's habitable zone, a fortunate position that has allowed oceans, weather, and life to thrive for billions of years. But here's where things get interesting when we compare our solar system to others. Many exoplanets discovered in their star's habitable zone aren't as welcoming as Earth. Take planets orbiting red dwarfs, the most common stars in our galaxy. These stars are smaller and cooler than our Sun, so their habitable zones are much closer in. That proximity comes with a catch. Gravitational forces can lock the planet's rotation, forcing one side to always face the star while the other remains in perpetual darkness. Imagine a world where one hemisphere is a scorching desert and the other a frozen wasteland, with only a thin ribbon of twilight in between where temperatures might be bearable. That's the reality for many tidally locked exoplanets. Even if such a planet has water, the extreme temperature divide could make it nearly impossible for life as we know it to take hold. The day side might lose its water to evaporation, while the night side could trap it as ice, leaving the surface barren. Adding to the challenge, red dwarfs are prone to violent flares that bombard nearby planets with radiation, stripping away atmospheres and sterilizing any chance of life. Compare that to Earth, where our Sun's steady energy output and our planet's gentle rotation create stable, global climates. Then there's the question of time. Our Sun's habitable zone has remained relatively stable over billions of years, giving life a long, uninterrupted window to evolve. But red dwarfs, despite their longevity, often start out as turbulent young stars, subjecting their planets to harsh conditions for the first few billion years. By the time they calm down, any early potential for life might have already been snuffed out. This isn't to say life couldn't exist under such extremes. Nature is full of surprises. But Earth's position in the habitable zone, combined with a stable star and a balanced rotation, creates an environment uniquely suited for the diversity of life we see today. When we look at exoplanets in their own Goldilocks zones, It's a stark reminder of how many factors had to align perfectly for our world to become the vibrant oasis it is. And that brings us to another key piece of Earth's puzzle, the remarkable features that set it apart from even the most promising rocky exoplanets. Now, let's take a closer look at what truly sets Earth apart from other rocky worlds, because even among planets in the habitable zone, our home stands out in remarkable ways. Earth isn't just a ball of rock with water. It's a dynamic, ever-changing world with features that create the perfect storm for life. First, consider plate tectonics. Earth's crust is broken into shifting plates that slowly move over millions of years, recycling materials between the surface and the mantle. This process isn't just geological trivia, it's vital for stabilizing our climate. Volcanic eruptions release carbon dioxide, which helps regulate temperatures, while the movement of plates also replenishes nutrients essential for life. But when we look at rocky exoplanets, especially super-Earths, planets with masses several times greater than ours, many seem to lack this mechanism. Without plate tectonics, their surfaces may become stagnant, with no way to recycle carbon or regulate heat. Some could even develop thick, rigid crusts that trap heat beneath, leading to catastrophic volcanic eruptions or a complete lack of geological activity. Then there's Earth's magnetic field, an invisible shield generated by the churning of molten iron in our core. This field deflects harmful solar radiation, protecting our atmosphere and surface life from being fried by charged particles. Without it, our planet might have ended up like Mars, a barren world whose atmosphere was stripped away over time by the solar wind. Many super-Earths, despite their size, may not have the right internal conditions to maintain a magnetic field. Some could be so massive that their high gravity prevents the convective motion needed to generate one, leaving them exposed and vulnerable. And let's talk about Earth's atmosphere, a delicate balance of nitrogen, oxygen, and trace gases that's neither too thick nor too thin. Compare that to the extremes we see in exoplanets. Some super-Earths have atmospheres so dense they create crushing surface pressures, turning what might have been oceans into supercritical fluids, a bizarre state between liquid and gas. Others have atmospheres stripped down to a whisper or worse, filled with toxic gases like hydrogen sulfide or carbon monoxide. Even planets with the right ingredients often lack the processes like Earth's carbon cycle to keep their atmospheres stable over billions of years. But Earth's uniqueness doesn't stop there. Our planet's size and gravity hit a sweet spot, strong enough to hold onto an atmosphere but not so strong that it becomes a crushing burden. Many super-Earths with their higher gravity could trap too much atmosphere, creating runaway greenhouse effects that turn them into Venus-like infernos. And while some exoplanets might have water, without Earth's perfect mix of geology, magnetism, and atmospheric chemistry, that water could be locked in ice, boiled away, or dissolved into a toxic soup. So when we marvel at the discovery of a rocky exoplanet in the habitable zone, it's worth remembering, Earth isn't just in the right place, it's built the right way. From its shifting continents to its protective magnetic embrace, our planet is a rare gem in a cosmos full of extremes. And that brings us to another silent guardian of Earth's stability, one we often take for granted but without which life as we know it might never have thrived. Now, let's turn our attention to a celestial partner that often goes unnoticed but plays a critical role in Earth's stability, the Moon. Without it, our planet would be a far more chaotic place. The Moon's most underrated gift, it acts like a cosmic anchor, stabilizing Earth's axial tilt. Right now, our planet leans at around 23.5 degrees, creating the predictable seasons we rely on for agriculture and climate stability. But without the Moon's gravitational influence, that tilt could wobble wildly, shifting by as much as 10 degrees or more over just a few thousand years. Imagine a world where seasons swing unpredictably between ice ages and scorching heat waves within human lifetimes. Some exoplanets, especially those without large moons, might experience exactly this kind of instability. Our moon's size is another key factor. It's unusually large compared to Earth, about 1/4 our planet's diameter, which gives it the gravitational muscle needed to keep our rotation steady. Contrast that with Mars, which has 2 tiny moons, Phobos and Deimos, neither of which can stabilize its axis. As a result, Mars' tilt can swing wildly over time, contributing to its drastic climate shifts. Some exoplanets might have even more extreme scenarios. Those with multiple moons could suffer from competing gravitational tugs, leading to erratic tilts and chaotic weather patterns. And then there's tidal locking, a phenomenon where a planet's rotation syncs up with its moon's orbit, always showing the same face to its companion. The moon is slowly doing this to Earth, but it's taking billions of years. Many exoplanets, especially those orbiting close to dim red dwarfs, could be tidally locked to their stars, with one side perpetually scorched and the other frozen. But our moon actually prevents Earth from becoming tidally locked to the sun by stirring our oceans and keeping our rotation dynamic. Without it, Earth might have faced the same fate, a day side too hot for life and a night side too cold. Even the moon's distance plays a crucial role. It's far enough to avoid destabilizing Earth's orbit, but close enough to exert significant influence. Some exoplanets have moons so close they trigger constant volcanic activity, like Jupiter's moon Io, but on a planetary scale. Others might have moons so distant they barely affect the planet's climate at all. Earth's moon, though, just right. So while we often focus on Earth's position in the habitable zone, we must also thank our fortunate partnership with the moon. Without it, our stable seasons, predictable climate, and even the tides that may have helped life begin could all be wildly different. And that's something worth remembering the next time you glance up at the night sky. Now let's dive into something so fundamental to life that we often take it for granted: water. On Earth, it flows freely in rivers, fills vast oceans, and even falls from the sky. But across the cosmos, water isn't just a simple liquid. It can take on forms and roles that defy imagination, and its distribution tells a fascinating story about how unique or chaotic a planetary system can be. Here's what sets Earth apart. Our planet is a Goldilocks world, not just in temperature, but in water balance. About 71% of Earth's surface is covered in liquid water, a rarity when you compare it to other known exoplanets. Many of these distant worlds have water, sure, but it's often locked away as vapor in scorching atmospheres, frozen into miles-thick ice sheets, or even mixed into lava oceans on superheated surfaces. Take, for example, the exoplanet JWST. This so-called water world might have entire oceans, but they're likely supercritical, meaning the water isn't quite liquid or gas, but something in between under crushing atmospheric pressures. Not exactly a vacation spot. Then there's the question of where water comes from in the first place. Earth's water may have arrived via ancient asteroid impacts during the solar system's chaotic early days. But exoplanetary systems, their water sources could be far more unpredictable. Some planets orbiting metal-poor stars might lack water entirely, while others in carbon-rich systems could have bizarre hydrocarbon lakes instead. Take Titan, Saturn's moon. Though not an exoplanet, it shows how alien water cycles can be, with methane rain and ethane rivers. Now imagine that on a planetary scale. But here's where Earth's water story gets even more interesting. It's not just about quantity, but location. Our oceans sit on the surface, interacting with the atmosphere and crust to create a stable climate. On tidally locked exoplanets, though, water might be trapped in eternal ice on the night side or boiled away on the star-facing side. And then there are lava planets like Kepler 10b, where any water would instantly vaporize in surface temperatures hot enough to melt rock. Even Earth's saltwater oceans play a special role. The salt content keeps water liquid at slightly lower temperatures, and ocean currents distribute heat globally, preventing extreme weather swings. Compare that to exoplanets where water might be pure, and thus freeze more easily or mixed with ammonia or other chemicals, creating slushy, semi-frozen seas. So next time you take a sip of water, remember, it's not just a drink, it's a cosmic luxury shaped by Earth's perfect storm of conditions. Out there among the stars, water is anything but ordinary, and that makes our pale blue dot all the more extraordinary. Now let's turn our attention upward to the very air we breathe. Earth's atmosphere isn't just a thin veil of gas. It's a dynamic, life-sustaining shield, and its composition is another piece of the puzzle that makes our planet so exceptional. Picture this, a delicate balance of 78% nitrogen, 21% oxygen, and trace gases like carbon dioxide and argon. This mix isn't just comfortable for us. It's a cosmic oddity when you stack it against the wild diversity of exoplanetary atmospheres out there. Take hydrogen-rich atmospheres, for example. Many gas giants and even some rocky exoplanets are swaddled in thick layers of hydrogen, the universe's most abundant element. On a planet like HD 189,733b, a cobalt-blue, hot Jupiter, hydrogen swirls in superheated winds laced with silicate particles that literally rain glass sideways. Not exactly breathable, then there are carbon dioxide-dominated atmospheres like the one enshrouding Venus, a cautionary tale of runaway greenhouse effects. But imagine a world where CO2 isn't just dominant but nearly pure, with pressures so high the gas turns into a supercritical fluid at the surface. That's the reality for some exoplanets, where the air itself behaves more like a liquid than a gas. But the true outliers are the worlds with metallic atmospheres. Yes, you heard that right, metallic. On ultra-hot Jupiters like WASP 76b, dayside temperatures soar so high, over 2,400 degrees Celsius, that iron vaporizes, creating clouds of molten metal that condense into iron rain on the cooler night side. Earth's gentle rainstorms, they'd seem downright quaint in comparison. Here's the kicker, though, an atmosphere isn't just about what's in it, it's about whether a planet can keep it. Atmospheric retention is where Earth shines again. Our magnetic field, generated by a churning molten core, deflects the solar wind's worst assaults, preventing our air from being stripped away over time. Mars wasn't so lucky billions of years ago. It likely had a thicker atmosphere, but without a strong magnetic shield, the solar wind eroded it into today's thin CO2 wisp. Now consider tidally locked exoplanets orbiting red dwarfs. Many are bombarded by relentless stellar flares, their atmospheres potentially shredded or vaporized over eons. Even if such a world started with an Earth-like air, it might end up as barren as Mercury. Yet Earth's atmospheric stability isn't just about defense. It's about chemistry in motion. Oxygen, for instance, is highly reactive without life's constant photosynthesis pumping it back in. Our atmosphere would lose its breathable balance in geologic eye blinks. Compare that to exoplanets where oxygen might build up abiotically, creating false biosignatures that tease astronomers with the idea of life. So when you step outside and take a deep breath, remember, that air is a masterpiece of cosmic engineering. Out there, atmospheres range from suffocating soups of methane to neon-lit metallic storms. But here, it's just right, another stroke of luck in our solar system's grand design. Now, let's shift our gaze from the skies above to the rocky remnants drifting between Mars and Jupiter, our asteroid belt. Far from the chaotic debris field Hollywood often portrays, this region is surprisingly orderly, with vast distances separating most of its inhabitants. Picture this, over 1 million asteroids, yet if you were to stand on one, your nearest neighbor might be millions of miles away. This sparse arrangement isn't just a cosmic accident. It's a frozen snapshot of our solar system's construction phase, where leftover material never coalesced into a planet, thanks to Jupiter's gravitational influence. But don't mistake tranquility for insignificance. These rocky fragments are cosmic time capsules holding clues to planet formation. Take Ceres, the belt's largest object, a dwarf planet with ice spewing cryovolcanoes and possibly a subsurface ocean. It's a relic of the early solar system, offering glimpses of how water and organic molecules were distributed. Even smaller asteroids like Ryugu and Bennu, sampled by recent missions, reveal amino acids, the building blocks of life. Far from a danger zone, our asteroid belt may have been a delivery service, ferrying water and minerals to a young Earth during the late heavy bombardment. Now contrast that with exoplanetary systems where asteroid belts are anything but benign. Imagine belts so dense they're more like celestial minefields. In systems like Epsilon Eridani, the asteroid belt is estimated to contain hundreds of times more material than ours, with collisions generating constant debris storms. For any nearby planets, this isn't just a nuisance, it's a hazard. Frequent impacts could strip atmospheres or sterilize surfaces, turning habitability into a cosmic lottery. Even worse, some systems exhibit extreme versions of our Kuiper belt, like Fomalhaut's sprawling disk, where asteroids collide with such violence they produce vast clouds of fine dust, visible from light years away. Then there's the wild card, migrating gas giants. In our solar system, Jupiter's stable orbit helped sculpt the asteroid belt into its current mild state. But in systems like HR 8799, where gas giants lurch inward, their gravity can fling asteroids into chaotic orbits, triggering bombardments that make our dinosaur-ending Chicxulub impact look like a pebble toss. Worse yet, some exoplanets orbit within their system's asteroid belts, enduring a perpetual hailstorm of rocky shrapnel. So while our asteroid belt is a quiet museum of solar system history, others resemble demolition derbies. That's yet another stroke of luck for us. No apocalyptic meteor showers, no relentless debris rain, just a distant rocky archive quietly orbiting the sun. And who knows, those unassuming space rocks might one day become stepping stones for human exploration, supplying resources for future missions. After all, in the cosmos, even the rubble has a story to tell. Now, let's journey beyond the asteroid belt to the solar system's frozen frontier, the Kuiper belt and the Oort cloud. These vast, icy reservoirs stretch far beyond Neptune, holding remnants of our solar system's birth and serving as cosmic warehouses for comets. Picture the Kuiper belt as a sprawling disk of frozen bodies, home to dwarf planets like Pluto and Haumea, while the Oort cloud is a distant spherical shell of icy objects stretching nearly halfway to the next star. Together, they're like nature's deep freezers, preserving pristine material from over 4.5 billion years ago. What makes these regions so fascinating? For starters, they're the source of many comets that occasionally visit the inner solar system. When a comet like Hale-Bopp or Neowise streaks across our sky, it's essentially a messenger from these icy outskirts, delivering clues about the early solar system's chemistry. The Kuiper belt, with its relatively stable orbits, acts as a conveyor belt for short-period comets, while the Oort cloud's loosely bound objects can be nudged into long, elliptical journeys toward the sun by passing stars or galactic tides. But how does this compare to exoplanetary systems? Here's where things get intriguing. While some exosystems, like HR 8799, show signs of distant debris disks resembling our Kuiper belt, others appear to lack these outer reservoirs entirely. Take, for example, the system around Vega, where the debris disk is so warm and close to the star that it suggests a complete absence of a cold, distant storage zone like ours. Without these icy reserves, such systems may lack the periodic comet showers that could deliver water and organic molecules to inner planets, a potential handicap for habitability. Even more striking are systems with multiple debris belts like Beta Pictoris, where nested rings of icy and rocky material create a complex gravitational dance. In such systems, comets might be hurled inward at erratic intervals, leading to unpredictable bombardments. Contrast that with our solar system's relatively orderly Kuiper belt, where Jupiter and Neptune act as gravitational gatekeepers, gently redirecting comets rather than launching them like cosmic catapults. Then there's the Oort cloud's uniqueness. No exoplanetary system has shown definitive evidence of an equivalent structure, likely because detecting such a diffuse, distant cloud is beyond current technology. But if others exist, they'd face challenges ours doesn't. In tightly packed systems or those near dense star clusters, passing stars could strip away these fragile comet reservoirs entirely, leaving nothing to seed future generations of icy visitors. So, while our solar system's outer reaches might seem like a quiet backwater, they're anything but insignificant. These icy archives not only shaped Earth's history, possibly delivering the water in our oceans, but also stand as another example of our cosmic good fortune. Other systems might have hotter, wilder debris disks or none at all, yet ours struck a delicate balance, distant enough to stay stable, but close enough to occasionally send us frozen time capsules from the solar system's infancy. And as we explore these frontiers with missions like New Horizons, who knows what other secrets these icy relics might reveal? Now, shifting our gaze to the motion of planets themselves, let's explore one of the most dramatic differences between our solar system and others' planetary migration. Here at home, our planets glide along their orbits with almost clockwork precision, their paths steady and predictable over billions of years. But out in the cosmos, many exoplanetary systems tell a far more chaotic tale, with planets that have been flung across their systems in gravitational upheavals. Take Jupiter as an example. In our solar system, it has maintained a stable orbit roughly 5 times Earth's distance from the Sun for eons. But in other systems, gas giants like Jupiter often don't stay put. Instead, they embark on epic inward journeys, becoming what astronomers call hot Jupiters, planets that scorch close to their stars, sometimes completing an orbit in just days. How does this happen? The answer lies in the delicate dance between a planet and the disk of gas and dust that surrounds a young star. In our solar system, Jupiter's migration was gentle, nudged by interactions with the debris disk, but ultimately settling into a harmonious position. In contrast, many exoplanetary systems show evidence of violent migrations, where planets spiral inward due to turbulent drag from the disk or gravitational tugs from sibling planets. The consequences of this chaos are staggering. A migrating gas giant can bulldoze through the inner system, ejecting smaller planets into deep space or plunging them into the star. Systems like HD 80606 showcase this drama. Its Jupiter-like planet follows a wildly elongated orbit, a relic of past gravitational battles. Compare that to our solar system, where Earth and its rocky neighbors have enjoyed serene orbits uninterrupted by such upheavals. This stability is no small factor in Earth's ability to nurture life. Even Neptune's story hints at migration, but of a far gentler kind. Scientists believe it may have formed closer to the Sun before drifting outward, a move orchestrated by gravitational teamwork with Jupiter and Saturn. This grand tack theory suggests our giants adjusted their orbits smoothly, like ships navigating a calm harbor. Meanwhile, exosystems like Upsilon Andromedae reveal the aftermath of planetary pinball, with multiple gas giants locked in unstable, overlapping orbits. What spared our solar system such turbulence? One theory points to our Sun's solitary nature, free from the gravitational meddling of a binary companion. Another credits the early disk's composition, which may have lacked the density gradients that trigger violent migrations elsewhere. Whatever the reason, the result is clear. Our planet's orderly orbits are a cosmic luxury. While other systems bear the scars of gravitational warfare, ours whispers a quieter, more enduring story, one where stability laid the groundwork for life. As we delve deeper into this cosmic contrast, we begin to see how even the motion of planets underscores our solar system's uniqueness. Far from being a universal rule, calm orbits like ours may be the exception rather than the norm. And that raises a tantalizing question. Did this serenity play a hidden role in Earth's habitability? The answer might just lie in the chaotic skies of distant exoplanets, where the ghosts of planetary migrations past still haunt the heavens. Now, let's turn our attention to another celestial quirk that sets our solar system apart: the quiet dominance of a single star. Unlike many exoplanetary systems which swirl around 2, 3, or even more stars, our Sun reigns alone, bathing its planets in steady light and predictable gravity. This solitude is rarer than you might think. In fact, astronomers estimate that around half of all Sun-like stars have at least one stellar companion, weaving a complex gravitational dance that can send planets into chaos. Take the Kepler-16 system, for example. Here, a planet orbits not one but two stars, locked in a celestial tug of war that bends its path into a stretched elliptical orbit. Seasons on such a world would be unpredictable at best, with light levels swinging wildly as the stars eclipse each other. Even more extreme is the case of HD 131399 AB, a planet caught in a triple star system. With gravitational forces pulling from multiple directions, its orbit is anything but stable, a far cry from Earth's steady, sunlit rhythm. Why does this matter? In binary or trinary systems, the gravitational push and pull between stars can yank planets from their original orbits, flinging them into deep space or plunging them into one of the stars. Some worlds end up on tilted, wobbly paths, while others are ejected entirely, becoming rogue planets adrift in the void. Contrast that with our solar system, where Earth's circular orbit has remained undisturbed for billions of years, thanks to the Sun's unwavering gravitational embrace. The challenges don't end there. In systems like Alpha Centauri, where three stars intertwine, the habitable zone, the region where liquid water could exist shifts constantly as the stars move. A planet might start in a life-friendly spot, only to be baked or frozen as stellar orbits shift. Our Sun, by contrast, offers Earth a Goldilocks zone that stayed just right for eons, allowing life to take root and thrive without such upheavals. Even the formation of planets becomes a high-stakes gamble in multi-star systems. The competing gravitational fields can tear apart the protoplanetary disks where planets are born, scattering material or preventing it from clumping together smoothly. Our solar system, free from such interference, had the luxury of forming planets in peace, with debris coalescing into orderly orbits over millions of years. This isn't to say binary systems can't host planets, far from it. Some, like Gamma Cephei, manage to harbor worlds in stable orbits by keeping their stars far apart. But these are exceptions. For every orderly multi-star system, countless others resemble gravitational roller coasters, where planets are passengers on a wild, unpredictable ride. So, what shielded our solar system from this fate? Pure cosmic luck, perhaps. The Sun may have formed in a sparser region of its stellar nursery, avoiding close encounters that could have bound it to a companion. Or maybe its birth cloud simply lacked the material to form a second star. Whatever the reason, the result is the same: a peaceful, single-star system where planets and life could flourish undisturbed. As we piece together these stellar stories, one truth becomes clear. The calm, predictable rhythms of our solar system aren't just a backdrop for life, they're a rare gift, one that countless exoplanetary systems never receive. And that invites us to wonder, in a universe teeming with stellar duos and trios, how many worlds out there yearn for the stability we take for granted? Now, let's consider another factor that shaped our solar system's uniqueness: its age and the surprising role of stardust. Our Sun isn't just a solitary star, it's also a cosmic elder with a metal-rich recipe that set the stage for planets like Earth. Born roughly 4.6 billion years ago, The Sun belongs to a generation of stars that formed after the universe had already been seeded with heavy elements, what astronomers call metals. These elements, forged in the hearts of earlier stars and scattered by supernova, became the building blocks for everything from Mercury's iron core to Earth's oceans. Compare this to younger stars hosting exoplanets today. Many of these stars are metal-poor, meaning they formed when the universe was still relatively pristine, lacking the abundance of heavy elements our solar system enjoys. Take the exoplanet host star Kepler 438, for example. This star is nearly 2 billion years younger than the Sun and has only about half its metal content. Planets orbiting such stars often end up with very different compositions. Think smaller cores, thinner atmospheres, or even worlds dominated by lightweight materials like water ice. Metallicity isn't just about ingredients, it's about opportunity. In the early universe, metal-poor stars struggled to form rocky planets at all. Without enough silicon, iron, and magnesium, their protoplanetary disks lacked the dense materials needed to clump into Earth-like worlds. Instead, they tended to spawn gas giants or sparse, icy bodies. Our Sun's metal-rich environment, by contrast, allowed for a diverse planetary menu: rocky inner planets, gas giants further out, and even the delicate balance of elements that made life possible on Earth. Age plays a role too. Older stars like the Sun had more time to collect metals from generations of supernova before forming. Younger stars, especially those in regions with less stellar activity, often miss out on this enrichment. The exoplanet system around the star TOI 560, for instance, is only about 1 billion years old. Its planets are still cooling from their fiery births, with surfaces likely molten and atmospheres still settling. Earth, by comparison, had billions of years to cool, stabilize, and develop the perfect conditions for life. But here's the twist: too many metals aren't always better. Stars with extremely high metallicity, like HD 10180, tend to overproduce gas giants. Their disks have so much solid material that Jupiter-like worlds form easily, often crowding out smaller rocky planets. Our Sun struck a rare balance metal rich enough to build Earth, but not so much that it choked the inner system with gas giants. This delicate interplay of age and metallicity highlights just how finely tuned our solar system is. It's not just about where the planets are today, but about the cosmic timing and chemistry that allowed them to exist in the first place. As we discover more exoplanets, we're learning that systems like ours, born in the right era with the right materials, are anything but common. And that raises a fascinating question. If the universe had stirred its stellar recipes differently, would we even be here to wonder about it? Now, let's turn our attention to a hidden architect of planetary systems: the ice line, an invisible boundary that played a pivotal role in sculpting our solar system's layout. Picture the early solar system as a swirling disk of gas and dust, with temperatures dropping sharply as you move away from the Sun. The ice line marks the point where it's cold enough for volatile compounds like water, ammonia, and methane to freeze into solid ice grains. In our solar system, this boundary lies between Mars and Jupiter, roughly where the asteroid belt is today. This frosty frontier wasn't just a curiosity, it was a cosmic sorting mechanism. Inside the ice line, where temperatures were too high for ices to survive, only metals and silicates could condense into solid particles. These dense materials clumped together to form the rocky planets: Mercury, Venus, Earth, and Mars. Beyond the ice line, water and other volatiles froze solid, adding vast amounts of material to the building blocks of planets. This allowed gas giants like Jupiter and Saturn to form massive cores quickly, scooping up enormous amounts of hydrogen and helium from the surrounding disk. But here's where our solar system stands out. Many exoplanetary systems have ice lines in radically different positions, leading to wildly different planetary arrangements. Take the young star HL Tau, for example. Its protoplanetary disk shows multiple ice lines at varying distances due to temperature fluctuations, creating concentric rings where different ices condense. This chaos often results in gas giants forming much closer to their stars, hence the prevalence of hot Jupiters in other systems. Even more striking is the case of red dwarf stars, which are cooler and fainter than our Sun. Their ice lines sit incredibly close to the star, sometimes within what would be Mercury's orbit in our system. Planets forming there end up with bizarre compositions, like water worlds with global oceans hundreds of miles deep or icy super-Earths with steam atmospheres. Compare that to Earth, where the ice line's distance allowed just the right amount of water to be delivered by comets and asteroids, enough for oceans but not enough to drown the continents. The ice line also influenced smaller bodies. In our solar system, the asteroid belt remains a relic of the ice line's dividing effect, too close to form icy worlds, too far to merge into a rocky planet. Meanwhile, exoplanetary systems with misplaced ice lines often lack such orderly debris fields. Some have asteroid belts drenched in ice, while others have none at all, their building blocks either swallowed by migrating planets or scattered into deep space. This cosmic zoning law didn't just shape our planets, it set the stage for life. Earth's position just inside the ice line meant it could accumulate water without becoming a snowball, while Jupiter's formation beyond it shielded us from excessive comet bombardments. In other systems where ice lines wobble or overlap with habitable zones, the outcomes are far less predictable. Some planets might oscillate between ice ages and greenhouse hells, while others could be locked in eternal frost or scorching vapor. So next time you sip a glass of water, remember, it's here because billions of years ago, the ice line in our solar system struck a perfect balance. And as we uncover more exoplanets, we're realizing just how rare that balance might be. Now let's venture into the cosmic wilderness to meet the ultimate wanderers, rogue planets. These are worlds untethered to any star, drifting endlessly through the dark expanse of interstellar space. Imagine a planet like Earth or Jupiter, but instead of orbiting a sun, it's completely alone, traveling through the void where temperatures hover near absolute zero. These nomads of the galaxy challenge our very definition of a planetary system, and their existence highlights just how orderly our solar system really is. Most rogue planets start out like any other, forming within a star's protoplanetary disk, but gravitational tugs from neighboring planets or passing stars can violently eject them, sending them careening into the abyss. Some might even form directly from collapsing gas clouds, never knowing the warmth of a parent star. In contrast, our solar system's planets have enjoyed remarkable stability for billions of years, their orbits finely tuned by gravity's delicate balance. Jupiter's gravitational dominance, for instance, acts like an anchor, preventing smaller bodies from being hurled into deep space. The scale of this cosmic exile is staggering. Astronomers estimate there could be billions of rogue planets in our galaxy alone, outnumbering stars by at least 2 to 1. Some, like the recently discovered free-floating planet CFPD Sir 2149, drift relatively close to us, just 100 light-years away. Others might be hurtling through the interstellar void, invisible to our telescopes because they emit no light of their own. What's fascinating is how these planets manage to survive without a star. While surface conditions would be unimaginably harsh, eternal darkness, temperatures hundreds of degrees below freezing, some rogue worlds might harbor hidden oceans beneath icy crusts, kept liquid by internal heat from radioactive decay or tidal forces. In theory, these subsurface layers could even support microbial life, a tantalizing possibility for astrobiologists. Compare that to Earth, where our sun's steady energy fuels ecosystems and drives weather cycles, making life as we know it possible. The presence of rogue planets also raises a haunting question. Could one ever visit our solar system? It's unlikely but not impossible. A passing rogue planet could disrupt the orbits of our own worlds, though the vast distances between stars make such encounters extraordinarily rare. Meanwhile, exoplanetary systems packed with closely spaced planets are far more vulnerable to ejections, which is why many exoplanet hunters find missing planets in systems where gravitational chaos seems to have cleared the neighborhood. Our solar system's serene architecture, with its well-behaved planets and predictable orbits, is clearly the exception, not the rule. Rogue planets remind us that the universe favors chaos over order, and that Earth's stable, sunlit corner of space is a rare and precious gift. So the next time you gaze at the night sky, consider the untold numbers of unseen worlds adrift in the darkness, and appreciate the delicate balance that keeps our planetary family safely together. Now, let's shift our gaze from the silent drifters of the cosmos to the chaotic skies of exoplanets, where weather defies all earthly logic. While we might grumble about a rainy day or a heat wave, the conditions on some distant worlds make our climate seem like a gentle breeze. Picture a planet where it rains diamonds, or where storms of molten glass rage sideways at thousands of miles per hour. These aren't scenes from science fiction, they're real, scientifically plausible phenomena happening right now in the universe, and they highlight just how tame and unique Earth's atmosphere truly is. Take the exoplanet WSP-76b, for example. This scorching gas giant orbits so close to its star that daytime temperatures soar above 2,400 degrees Celsius, hot enough to vaporize metals. Here, iron isn't a solid or even a liquid. It's a gas, condensing into glittering iron clouds on the cooler night side before raining molten metal. Meanwhile, on planets like HD 189733b, winds scream at speeds over 5,000 miles per hour, carrying silicate particles that form into droplets of molten glass, hurled horizontally in endless, punishing storms. Even the diamond rain hypothesized on ice giants like Neptune seems quaint compared to the carbon-crushing pressures of a super-Earth like 55 Cancri e, where astronomers believe carbon atoms might compress directly into diamond crystals in the atmosphere. Earth, by contrast, is a haven of moderation. Our weather extremes, hurricanes, tornadoes, droughts are fleeting disturbances in a mostly stable system. Our atmosphere's nitrogen-oxygen mix, paired with just the right amount of greenhouse gases, creates a Goldilocks balance that sustains liquid water and diverse ecosystems. Exoplanets, however, often lack such equilibrium. Tidal locking, where one side of a planet permanently faces its star, can create permanent hurricanes on the day side, while the night side freezes in perpetual darkness. Others, like Kepler 7b, boast clouds made of vaporized rock floating in skies so hot they glow like embers. What's truly striking is how these extreme conditions arise from fundamental differences in planetary makeup. Many exoplanets, especially hot Jupiters, have atmospheres dominated by hydrogen or helium, lacking the complex chemistry that buffers Earth's climate. Others, like GJ1214b, might be water worlds with steamy, high-pressure atmospheres where water exists as a supercritical fluid, neither liquid nor gas. Even magnetic fields play a role. Without Earth's protective magnetosphere, many exoplanets are bombarded by stellar winds, stripping away their atmospheres or triggering relentless auroras that light up their skies with eerie, non-stop electrical storms. Yet, for all their fury, these exotic worlds teach us a humbling lesson. Earth's mild weather isn't just a happy accident, it's the product of a finely tuned system where distance from the sun, atmospheric composition, and planetary dynamics align perfectly. While exoplanets dazzle us with their extremes, they also underscore a profound truth. In the vastness of space, a planet as hospitable as ours is the rarest weather report of all. Now, let's turn our attention to another cosmic quirk that sets our solar system apart, the gentle tug of tidal forces. While Earth experiences mild ocean tides thanks to the Moon's pull, many exoplanets endure gravitational stresses so intense they reshape entire worlds. Imagine a planet stretched like taffy, its surface cracking under the strain, or one side permanently scorched while the other freezes solid. These aren't hypothetical scenarios, they're everyday realities for planets trapped in extreme orbital dances. Take Jupiter's moon Io as a starting point. Its volcanic chaos, driven by Jupiter's gravity, is the closest thing we have to tidal extremes in our solar system. Yet even Io's fiery spectacle pales next to exoplanets like Proxima Centauri b, where tidal locking forces one hemisphere to eternally face its red dwarf star. The result, a planet split into two brutal halves, a scorching desert on the day side and a frozen wasteland on the night side, with no twilight zone in between. Unlike Earth's balanced rotation, which distributes sunlight evenly, these worlds are cosmic prisoners of gravity's grip, but tidal locking is just the beginning. Some exoplanets, like those in close orbits around pulsars, endure even wilder distortions. Picture WST-12b, a gas giant so close to its star that gravity stretches it into an egg shape, stripping away its atmosphere in a glowing trail. Meanwhile, planets in multi-star systems face gravitational tug-of-wars, their orbits jerked unpredictably by competing stellar pulls. Compare this to our solar system's orderly rhythms, where Earth's stable rotation and the Moon's gradual retreat, just 1.5 inches per year, feel almost leisurely. Orbital resonance adds another layer of intrigue. In our solar system, Neptune and Pluto's graceful 2 to 3 resonance keeps their paths harmonized without chaos. But many exoplanets, especially in compact systems like TRAPPIST-1, are packed so tightly that their gravitational interactions create heat through friction. Imagine a planet where the ground itself warms from constant gravitational kneading, like dough in an oven. This tidal heating can trigger subsurface oceans or even volcanic eruptions, turning what might have been a habitable world into a pressure cooker. The lesson here is profound. Earth's quiet orbit and gentle tides aren't just conveniences, they're foundational to life's stability. While exoplanets dazzle us with their gravitational dramas, they remind us that our solar system's subtle, balanced forces are a rare cosmic gift. From the Moon's steadying influence to the absence of crushing tidal heats, these quiet details make our corner of the universe uniquely hospitable in a galaxy full of gravitational extremes. Now, let's consider the recipe for life itself, a delicate blend of ingredients that Earth seems to have mixed just right. While the universe is teeming with planets, very few offer the precise conditions needed to whip up something as complex as life. Earth's recipe card reads like a cosmic miracle: carbon for structure, water as a universal solvent, nitrogen and phosphorus for genetic blueprints, and just the right amount of energy from the sun. But out there among the exoplanets, the kitchen looks very different. Take carbon, for example. It's the backbone of life on Earth, forming everything from DNA to cell membranes. Yet on planets like 55 Cancri e, carbon is so abundant that scientists speculate it could rain diamonds. Imagine a world where the very element that builds life here becomes a crushing, glittering weight, a far cry from Earth's balanced carbon cycle. Then there's water, our liquid lifeline. While Earth's surface is 70% water, exoplanets like JWST might harbor it in supercritical states, where it's neither liquid nor gas but a scalding, corrosive fluid. Others, like those near dim red dwarfs, could have all their water frozen on one side and boiled away on the other, leaving no Goldilocks zone in between. But it's not just about having the right ingredients, it's about keeping them in the right proportions. Earth's atmosphere is a gentle mix of nitrogen and oxygen, but on Venus, a thick blanket of carbon dioxide creates a runaway greenhouse effect, turning the planet into a pressure cooker. Meanwhile, exoplanets like HD 189733b whip up hurricanes of molten glass in methane-rich skies, a far cry from Earth's life-friendly air. Even trace elements matter. Without phosphorus, there'd be no energy-carrying molecules like ATP. Yet some exoplanets, like those orbiting metal-poor stars, might lack this critical spark entirely. Then there's the question of delivery. Earth likely received its water and organic molecules from asteroids and comets, a gentle cosmic grocery run. But in systems like Beta Pictoris, young planets are bombarded by massive, volatile, rich asteroids at speeds that would sterilize any budding life. And while Earth's magnetic field shields its ingredients from being stripped away by solar winds, airless exoplanets like Co-Rho T7b have no such protection, their surfaces scoured clean by their stars. What makes Earth's recipe truly special isn't just the ingredients list, it's the stability to let them simmer. Plate tectonics recycle nutrients, the moon stabilizes our climate, and the sun provides steady energy without deadly flares. Contrast that with exoplanets like Kepler 78b, where surface temperatures exceed 2,000 degrees, or icy rogue planets drifting starless in the void. Life's recipe isn't just rare, it requires a kitchen that stays standing long enough to bake. So while the universe might be full of potential ingredients, Earth reminds us that the real magic lies in how they're measured, mixed, and maintained over billions of years. Now, let's turn our attention to another silent guardian of our solar system, the invisible force of magnetic fields. While we often think of planets as solid, static worlds, many of them hum with powerful magnetic personalities, and this hidden trait plays a starring role in keeping life possible. Earth, for instance, is wrapped in a protective magnetic bubble, shielding us from the sun's relentless barrage of radiation. Without this shield, our atmosphere would be stripped away, leaving the surface exposed to deadly cosmic rays. Jupiter takes this defense to an even grander scale, with a magnetic field so strong it creates auroras brighter than the sun and deflects radiation that could otherwise fry its moons. But not all planetary systems are so fortunate. Out among the exoplanets, many worlds orbit stars far more volatile than our sun. Red dwarfs, for example, which are notorious for unleashing devastating flares. Planets like Proxima Centauri b, despite sitting in the habitable zone, are routinely scorched by these eruptions, their atmospheres blasted away by streams of charged particles. Without a robust magnetic field, even a planet with the right ingredients for life becomes a barren wasteland. Some exoplanets might generate weak magnetic fields, but if their host star is too active, like the hyperflare star Kepler 438, the protection simply isn't enough. Then there's the question of how these magnetic fields are born. Earth's field comes from its churning molten iron core, a dynamo effect that acts like a giant planetary generator. Gas giants like Jupiter generate theirs through layers of metallic hydrogen deep within their interiors. But what about rocky exoplanets slightly larger than Earth, so-called super-Earths? Their immense gravity could crush their cores into unusual states, potentially stifling magnetic dynamos altogether. And tidally locked planets, forever facing their star with one side, might have lopsided or non-existent magnetic fields, leaving them defenseless. The consequences of a missing or weak magnetic shield are dire. Take Mars, a cautionary tale in our own backyard. Billions of years ago, it likely had rivers and lakes, but as its core cooled and its magnetic field faded, solar winds clawed away its atmosphere, turning it into the frozen desert we see today. Now imagine that process on an exoplanet bombarded by flares hundreds of times stronger than our sun's. Even if life somehow emerged, it wouldn't stand a chance. Yet here's where our solar system's magnetic personalities shine. Earth's field not only guards our atmosphere, but also steers charged particles toward the poles, creating the dazzling auroras that light up our skies. Jupiter's colossal magnetosphere even shelters its icy moon Europa, potentially preserving its subsurface ocean, a tantalizing hint that magnetic protection might extend life's reach beyond the traditional habitable zone. So while the universe is full of planets, the ones with the right magnetic chemistry to nurture and shield life, that's a rarity worth celebrating. Now let's take a step back and consider a question that has puzzled scientists for decades: where is everybody? This is the heart of the Fermi Paradox, the stark contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it. If the universe is teeming with planets, and many of them fall within habitable zones, why haven't we detected any signs of advanced civilizations? Our solar system's unique features might hold a clue to this cosmic mystery. Think about it. Earth isn't just a lucky accident, it's the product of an extraordinary chain of finely tuned conditions. The right star, the right planetary arrangement, the right magnetic shields, and even the right moon. But when we look at exoplanetary systems, these perfect alignments seem rare. Hot Jupiters dominate close orbits, tidal locking turns potential paradises into scorched or frozen wastelands, and violent stellar flares strip away atmospheres. Even if life emerges on some of these worlds, the odds of it surviving long enough to evolve into something we could detect are vanishingly slim. Consider the Great Filter Hypothesis, one possible answer to the Fermi Paradox. It suggests that somewhere along the path from simple chemistry to interstellar civilization, there's a barrier so extreme that almost no life gets past it. Is that filter behind us, meaning with a rare exception, or is it ahead, waiting to wipe us out? Our solar system's stability might mean we've already cleared some of these hurdles, like avoiding early atmospheric loss or dodging a migrating gas giant that could have flung Earth into oblivion. But exoplanetary systems, with their chaotic orbits and extreme environments, might hit that filter far more often. Then there's the issue of time. Our Sun is middle-aged, and Earth took billions of years to develop complex life. But many exoplanets orbit red dwarfs, which can burn for trillions of years. If life arises there, why hasn't it had time to reach us? Perhaps because red dwarfs are turbulent, frying their planets with flares before life can gain a foothold. Or maybe advanced civilizations are just too short-lived, self-destructing before they can colonize the stars. But here's the hopeful twist. Our solar system's uniqueness doesn't necessarily mean we're alone. It might mean we're looking in the wrong places. Most exoplanet searches focus on Earth-like worlds around Sun-like stars, but life could thrive in ways we haven't imagined. Subsurface oceans on icy moons, silicon-based organisms in extreme heat, or even rogue planets drifting between stars with internal heat sources. The paradox forces us to question our assumptions and widen the search. So while our solar system stands out as a rare gem, it also reminds us how little we know. Every strange exoplanet discovery chips away at the paradox, offering new pieces to the puzzle. The silence isn't necessarily emptiness, it might just be a sign that we're only beginning to learn the rules of this cosmic game. But let's not forget our search for answers is only as sharp as the tools we use. Right now, even with groundbreaking instruments like the James Webb Space Telescope, our understanding of exoplanets is like looking through a frosted window. We can see shapes, estimate sizes, even catch glimpses of atmospheres, but the finer details, those remain frustratingly out of reach. Take atmospheric analysis, for example. When we study exoplanets, we're often relying on indirect methods. The transit technique, where a planet passes in front of its star, gives us clues about its atmosphere by measuring how starlight filters through it. But this is like trying to guess the ingredients of a soup by sniffing the steam. The James Webb Telescope has revolutionized this, detecting molecules like water vapor and carbon dioxide, but it's still limited. For smaller, Earth-sized planets, the signals are whisper-thin, drowned out by stellar noise or lost in the glare of their host stars. Compare that to our solar system, where we've sent probes to taste the atmospheres of Venus or Mars directly, or even land on them. Then there's the challenge of distance. The closest exoplanet we've found, Proxima Centauri b, is still 4.2 light-years away. That's 25 trillion miles, so far that even our most powerful telescopes struggle to resolve its surface features. Imagine trying to study a single light bulb on a distant mountain while blinded by a spotlight. That's the scale we're working with, In contrast, every planet in our solar system has been photographed, mapped, or visited by spacecraft, giving us crystal-clear data. Resolution is another hurdle. Even the James Webb Telescope can't take a crisp photo of an exoplanet's surface. Instead, we piece together rough estimates, like inferring a planet's temperature based on its orbit or guessing its composition from spectral lines. This means we might mistake a lava world for a water world, or overlook subtle signs of life because our tools aren't sensitive enough. Remember how Mars, once thought to have canals, turned out to be a dusty desert. Now magnify that uncertainty across light years and let's talk time. Observing exoplanets requires patience. A single transit might last hours, and full atmospheric studies demand multiple passes, sometimes years of waiting. Meanwhile, changes in a star's brightness or cosmic interference can corrupt the data. Compare that to studying Jupiter's storms with the Juno probe, which sends back real-time updates. Our solar system is like having a front-row seat to a concert, while exoplanets are muffled echoes from the parking lot. But here's the silver lining: every limitation is a roadmap for tomorrow's technology. Future missions like the Habitable Worlds Observatory aim to directly image Earth-like planets, while advanced spectrographs could sniff out biosignatures with unprecedented precision. For now, the gaps in our knowledge remind us to stay humble. The universe isn't withholding its secrets, it's just waiting for us to build better tools to uncover them. So while our solar system remains the gold standard for comparison, the very imperfections in our exoplanet studies highlight how much more there is to discover. Each fuzzy data point is a puzzle piece, and every technological leap brings us closer to seeing the full picture. The cosmos isn't silent, we're just learning how to listen. Yet as we push the boundaries of current technology, a new wave of missions stands poised to shatter those limitations and bring exoplanets into sharper focus than ever before. Imagine stepping from a dimly lit room into broad daylight. That's the level of clarity these next-generation projects promise. Leading the charge is the Pluto mission, set to launch in 2026. Unlike its predecessors, Pluto won't just hunt for planets. It'll scrutinize their host stars with unprecedented precision. By studying stellar vibrations, it can determine a planet's age, composition, and even the likelihood of plate tectonics, key ingredients for habitability. Picture it as cosmic detective work, where tiny wobbles in starlight reveal whether a distant world has the stability to nurture life. Then there's Ariel, the European Space Agency's atmospheric sleuth. Slated for 2029, this trailblazer will perform the first large-scale survey of exoplanet atmospheres, analyzing the chemical fingerprints of around 1,000 worlds. Think of it as a celestial weather report, decoding whether a planet is shrouded in methane storms or blanketed by carbon dioxide, Ariel's secret weapon. Its ability to observe planets across a staggering range of temperatures, from scorching lava worlds to frozen giants. This means we'll finally understand how atmospheric chemistry shifts from one extreme to another, and where Earth-like conditions might hide. But the real game-changer could be the Habitable Worlds Observatory, NASA's ambitious plan for the 2030s. This isn't just another telescope. It's designed to block out starlight so effectively that it can directly image Earth-sized planets in the habitable zones of nearby stars. For the first time, we might see continents, clouds, or even hints of vegetation light years away. It's like upgrading from hearing a faint radio signal to watching high-definition video of another world. Meanwhile, ground-based innovations are equally groundbreaking. The extremely large telescope, now under construction in Chile, will combine 39-meter mirrors with adaptive optics to cancel out atmospheric blur. The result, images of exoplanets with details sharp enough to track seasonal changes or detect ocean glints. And let's not forget the Square Kilometre Array, a global radio telescope network that could eavesdrop on exoplanetary magnetic fields, potential lifelines against deadly solar radiation. What ties these missions together is their shared goal: transforming exoplanets from blurry dots into living, dynamic worlds. With Pluto, we'll grasp how planetary systems form. Ariel will expose the diversity of alien skies. The Habitable Worlds Observatory might finally answer whether we're alone. Each mission builds on the last, threading individual discoveries into a grand cosmic narrative. So while today's tools leave us squinting at shadows, tomorrow's technology will fling open the curtains. The universe isn't just showing us exoplanets, it's inviting us to understand them. And with every mission, we're not just observing the cosmos, we're learning to read its stories. But while these missions bring distant worlds into focus, let's shift our gaze closer to home, because even within our own solar system, colonization is no easy feat. Take Mars, humanity's most promising off-world destination. Temperatures average -60 degrees Celsius, the atmosphere is lethally thin, and dust storms can engulf the entire planet for months. Yet compared to Proxima Centauri b, Mars might as well be a tropical resort. Proxima Centauri b orbits a red dwarf star just 4.2 light-years away, technically in the habitable zone. But habitable here is a stretch. The planet is likely tidally locked, with one side eternally scorched and the other frozen. Solar flares from its star bombard it with radiation hundreds of times stronger than anything Earth experiences, stripping away atmospheres and dousing surfaces in deadly ultraviolet light. Colonizing it wouldn't just require domes or underground bunkers, it would demand technology to entirely remake a hostile world. Now consider Europa, Jupiter's icy moon. Its subsurface ocean, warmed by tidal forces, could harbor life. But reaching that ocean means drilling through kilometers of ice under crushing pressure, all while dodging Jupiter's radiation belts. Still, Europa's challenges pale next to the hurdles of exoplanet colonization. Imagine sending humans to Proxima Centauri b. Even at 10% the speed of light, the journey would take 42 years, generations living and dying in transit. And if they arrived, no resupply missions, no emergency returns, just an irradiated, gravitationally tortured world where every breath of air must be manufactured. Mars and Europa offer harsh but surmountable problems. We can test solutions locally, building radiation shields, growing food in regolith, or tapping Europa's ice for water. Mistakes, a rescue mission might take months, not millennia. But exoplanets demand leaps in technology we've barely dreamed of: FTL propulsion, artificial gravity, planetary scale terraforming. Until then, they remain tantalizing but treacherous destinations. Here's the sobering truth: our solar system, for all its extremes, is a gentler nursery for spreading life than the galaxy's so-called habitable exoplanets. That doesn't mean we'll never reach them, just that we'll master our cosmic backyard first. Every challenge we conquer on Mars or Europa is a stepping stone to the stars. Now let's take a step back and consider a fascinating idea that ties everything together: the rare Earth hypothesis. This theory suggests that Earth's extraordinary mix of conditions might not just be lucky, but almost impossibly rare in the cosmos. Think about it, our planet sits in a perfect sweet spot, not too close to the sun and not too far, with just the right amount of liquid water, a protective magnetic field, and a stabilizing moon. But here's the kicker: each of these factors isn't just nice to have, they're critical for complex life, and the chances of them all aligning elsewhere might be vanishingly slim. Take plate tectonics, for example. Earth's shifting crust recycles nutrients, regulates carbon dioxide levels, and even helps maintain our magnetic field. Without it, our atmosphere could erode, temperatures might swing wildly, and life as we know it would struggle to survive. Yet most rocky exoplanets we found show no signs of this geological engine. Some are so still their surfaces resemble a single, unbroken slab of rock, while others have volcanic chaos that would make Earth's eruptions look tame. Then there's Jupiter, our solar system's silent guardian. Its massive gravity acts like a cosmic vacuum cleaner, pulling in asteroids and comets that might otherwise bombard Earth. In exoplanetary systems, gas giants often migrate inward, becoming hot Jupiters that disrupt the orbits of smaller planets or even fling them into space. Imagine an Earth-like world constantly knocked off course by a neighboring giant, hardly a stable home for life to take root. Even Earth's atmosphere is a delicate balancing act. Our nitrogen-oxygen mix isn't just breathable, it's also chemically stable, shielding us from solar radiation while allowing just enough sunlight through for photosynthesis. Compare that to exoplanets with hydrogen-dominated skies where the air is thick and crushing, or those with carbon dioxide atmospheres dense enough to turn rain into corrosive acid. And let's not forget our ozone layer, a fragile shield that took billions of years to form and exists nowhere else we've looked. The moon, often taken for granted, is another unsung hero. Its gravity stabilizes Earth's axial tilt, preventing extreme climate swings that could turn continents into deserts or ice sheets overnight. Many exoplanets either lack moons entirely or have multiple satellites tugging them chaotically, leading to wild seasonal shifts that would make agriculture, let alone civilization, nearly impossible. So what does this all mean? The rare Earth hypothesis argues that while microbial life might be common, the leap to complex organisms, let alone intelligent beings, could depend on a checklist of cosmic coincidences that Earth just happens to meet. It's not just about being in the habitable zone. It's about having the right star, the right neighbors, the right geology, and even the right history. Does this make Earth special? Absolutely. But it also raises a profound question. If we're the result of such a narrow set of circumstances, what does that say about the search for life beyond our solar system? Every discovery of a potentially habitable exoplanet reminds us that habitability isn't just about distance from a star. It's about a symphony of factors working in harmony. And right now, Earth seems to be playing a very solo tune. Now, here's something that might make you rethink the rare Earth hypothesis: sheer numbers. With over 5,000 exoplanets already discovered and billions more likely out there, some scientists argue that even if Earth-like conditions are rare, the universe's vastness might still make life inevitable. Imagine flipping a coin 1 trillion times. Even the unlikeliest outcomes become probable eventually. Take the Kepler mission's findings, for example. It revealed that rocky planets in habitable zones are far more common than we once thought. While many of these worlds don't mirror Earth exactly, they hint at the universe's creative flexibility. A planet might lack plate tectonics but have deep underground oceans heated by geothermal vents like Jupiter's moon Europa. Or consider tidally locked exoplanets where one side permanently faces their star while the day side might be scorching. The terminator line between light and dark could harbor temperate zones where life adapts to eternal twilight. Then there's the resilience of life itself. On Earth, extremophiles thrive in boiling acid, crushing ocean depths, even the vacuum of space. If life can persist here under such brutal conditions, why couldn't it evolve under radically different skies? An exoplanet with a methane atmosphere might host organisms that breathe it like we do oxygen. Hydrogen-dominated worlds could foster life forms with biochemistry we've never imagined. The universe doesn't need to follow Earth's recipe to cook up something extraordinary. Even our solar system offers surprises. Mars once had flowing rivers, and Venus, now a hellscape, may have been habitable for billions of years before its greenhouse effect spiraled out of control. If life emerged there and clung on in microbial refuges, it would mean 2 potentially habitable worlds orbiting the same star. Extend that logic to the countless multi-planet systems we've found, and the odds look less daunting. Critics of the rare Earth hypothesis also point to convergent evolution, the way nature independently crafts similar solutions, like wings evolving in birds, bats, and insects. If life arises elsewhere, might it too develop intelligence, technology, or even civilization, just through different pathways? Dolphins and octopuses show complex behavior without hands or tools. An alien species could surpass us using senses or abilities we can't fathom. So where does this leave us? The debate isn't about whether Earth is special, it clearly is, but whether its uniqueness is a cosmic fluke or one variation in a grander tapestry. With next-gen telescopes like the Habitable Worlds Observatory set to analyze exoplanet atmospheres for biosignatures, we might soon have data to tip the scales. Until then, the universe keeps whispering two possibilities. Either we're a statistical miracle, or life out there is waiting in forms we've yet to recognize. Either way, the search is far from over. Now, stepping back from the science for a moment, let's consider something equally profound: how the uniqueness of our solar system has shaped not just our understanding of the cosmos, but our very identity as a species. For millennia, humans have looked up at the night sky and wondered, are we alone? Is Earth a rare sanctuary or just one thread in a vast cosmic tapestry? These questions don't just drive scientific inquiry, they've inspired art, philosophy, and even our sense of purpose. Take the ancient Greeks who imagined the planets as wandering gods, or the Renaissance thinkers like Copernicus, who dared to place the sun at the center of our system, demoting Earth from its privileged position. Each revelation about our solar system has forced us to reconsider our place in the universe. When Galileo pointed his telescope at Jupiter and saw moons orbiting another world, it shattered the idea that everything revolved around us. Fast forward to today, and the discovery of exoplanets has done something similar. It's shown us that our solar system isn't the default template, but one of countless possibilities. This realization sparks both humility and ambition. Humility because it underscores how small we are in the grand scheme, yet ambition because it fuels our desire to explore. Think of the Voyager probes carrying golden records with sounds and images of Earth into interstellar space, a message in a bottle tossed into a cosmic ocean. Or the Mars rovers scouring another world for clues about life. These missions aren't just scientific endeavors, they're expressions of a species yearning to connect, to understand, and perhaps to find neighbors in the void. Culturally, our solar system's uniqueness has become a mirror. Some see it as evidence of a finely tuned universe, a narrative that resonates with spiritual or philosophical beliefs in intentional design. Others view it as a challenge, proof that life, if it exists elsewhere, must be wildly different, pushing us to expand our definitions of what life or intelligence could even mean. Science fiction, from Star Trek to Arrival, thrives on this tension, imagining aliens that reflect our hopes, fears, and creativity. And then there's the philosophical weight of our solitude. If Earth is truly one of a kind, what responsibility does that place on us? The overview effect reported by astronauts, the profound shift in awareness that comes from seeing Earth as a fragile, isolated speck, highlights this. Our solar system's rarity isn't just a fact, it's a call to stewardship, urging us to protect our pale blue dot because, for all we know, it might be the only one like it. Yet, paradoxically, the search for exoplanets also unites us. Missions like the James Webb Space Telescope are global efforts transcending borders. The question, are we alone, is perhaps the most universal one humanity has ever asked. Whether the answer is yes or no, the pursuit itself reminds us of our shared curiosity, our collective wonder. So as we marvel at the quirks of our solar system, its orderly planets, its protective Jupiter, its life-nurturing Earth, we're also marveling at ourselves. Every discovery, every mission, every debate about rarity or abundance is part of a larger story, humanity's endless quest to find meaning among the stars. And that, in the end, might be the most unique thing of all. Now, as we bring our cosmic journey to a close, let's reflect on what makes our solar system truly extraordinary. From the sun's steady brilliance to Earth's delicate balance of conditions for life, every detail sets us apart. Unlike the chaotic dances of exoplanetary systems, our planets move in harmonious, spacious orbits, with Jupiter standing guard against celestial threats. Our moon stabilizes Earth's tilt, and our asteroid belt remains a quiet relic of formation rather than a hazard. Even the water that blankets our world is a rare luxury compared to the extremes of lava oceans or ice-locked exoplanets. But uniqueness isn't just about geography, it's about meaning. Our solar system's architecture has shaped human history from ancient myths to cutting-edge science. It's pushed us to question, explore, and redefine our place in the universe. Whether you see its fine-tuned features as cosmic luck or something deeper, one truth remains: Earth, for now, is the only home we know. And that realization carries both wonder and responsibility. So here's a question to leave you with. What other secrets might our solar system hold? Could there be undiscovered worlds lurking in the Oort cloud, or clues about life hidden in Martian soil? The search is far from over. Every mission, every telescope brings us closer to answers and perhaps new mysteries. If this journey through the cosmos sparked your curiosity, don't stop here. Share your thoughts in the comments. Do you think life exists beyond our solar system, or is Earth truly one of a kind? And for more deep dives into space, science, and the universe's greatest puzzles, hit subscribe and ring the bell so you never miss an exploration. Together, let's keep looking up and asking the big questions. After all, the stars have never been closer.